Okay. Hello, everyone. Good morning, all of you. And today is the birthday of the great Bharat Ratna M.S. Subbulakshmi. She's a great singer, very, very great. And that's why she is given Bharat Ratna. She is unquestionably one of the greatest exponent of Carnatic music. And she was an Indian Carnatic singer from Madurai, Tamil Nadu. She was the first musician ever to be awarded the Bharat Ratna, India's highest civilian honor. She is the first Indian musician to receive the Raman Magsaysay Award, often considered as Asia's Nobel Prize in 1974, with the citation reading, exacting purists acknowledge Srimati M.S. Subbulakshmi as the leading exponent of classical and semi-classical songs in the Carnatic tradition of South India. And she was the first Indian who performed the United Nations General Assembly in 1966. Okay, so she is a great personality and she is born today. Okay, last class, what we have done is initially we have derived vorticity transport equation and stream function equation. As I told many times for mainly 2D incompressible flows, giving boundary condition of pressure is very difficult, and sometimes pressure is not important. I am interested in only velocity, suppose. Then there is a way of eliminating pressure from the continuity momentum equations. Okay, and so what we do is we take the curl of the momentum equation so that del cross del p becomes 0, and we are going to get del cross v's in different terms, so which is omega. So we are going to get vorticity transport equation. And if you solve that, I get vorticity, but I am interested in velocities. So for that, we take the vorticity equation or vorticity definition, dou v by dou x minus dou u by dou y equal to omega. So that v and u, if I substitute the definitions of stream function there, I'm going to get del square psi equal to minus omega, which is the stream function equation. So knowing omega from the vorticity transport equation, if I solve it, I'm going to get stream function. And once you get stream function, the derivatives of stream function, you will get u and v. Okay, that is the way we have to go about it. And we have derived the total energy equation, and which comes like, okay, these are the momentum equations in primitive variables in conservation form, substituting all the shear stresses and all. And the total energy equation we get like this. Okay, this is the time rate of change of energy within the control volume, and this is the heat generation, and this is the heat transfer by conduction, and this is the work transfer by pressure forces here and the viscous forces here, plus the work transfer due to body forces. Okay, so this is the total energy equation in the non-conservation form because of this total derivative here. And if I expand this into local derivative and the convective derivative, keeping the right hand side as it is, I'm going to get the conservation form. So this is the local derivative and this is the convective derivative. This is in conservation form. But many times I'm interested in getting the energy equation for internal energy. So I have to subtract this. So this can be obtained by multiplying x momentum equation by u, y momentum equation by v, and w with the z momentum equation, and adding them, you are going to get the d of v square by 2. And if I subtract, then I'm going to get the internal energy equation in non-conservation form. And again, this dE by dt, if I expand, I'm going to get in the conservation form like this. So the thing is, if you observe this, I'm going to eliminate body forces in the internal energy equation. And then by substituting E is equal to CVT, so we have seen that this can be, and assuming there is no convection and the pressure things, I'm going to get three-dimensional heat conduction equation from here. Okay, and we have general comments on the governing equation. These things I told initially, all the system of Navier-Stokes equations together, they are coupled system of nonlinear partial differential equations. Okay, so that is one of the main characteristic of this. It is nonlinear partial differential equations, and they are coupled each other because it depends. So you have to calculate some variables from one equation and substitute those variables in the other equation, and they are coupled. And so the differential equation, the difference between non-conservation and conservation forms lies only on the left-hand side. Okay, if I have total derivative, it is a non-conservation form. If it is in the local and convective derivatives divided, then it is conservation form. And in the left-hand side, if you see, I'm going to get so dou rho by dou t plus del dot rho v equal to 0. This is continuity. And dou of rho v by dou t plus del dot rho v is equal to minus del p plus del p. And if I write something like this, okay, something like this we are going to get. What I want to just say is, here I'm going to get divergence of something, okay, on the left hand side. So that's why sometimes these are called as divergence form of equation. The conservation form of equations are called as divergence form of equations, because the left hand side of the conservation form of equations contain the terms in the divergence form, and for this reason they are called as divergence form. Okay, and the number of variables rho, u, v, p, w, and here e and t is there because it is expressed in e, but I am interested in t, so I have to have additional equation e equal to cvt. Okay, and because I have now the one equation less, so that's why p equal to rho rt is another equation. So in this way, I am having a closed form of equations. And in fluid mechanics, as I told, only momentum equations are called Navier-Stokes equations, whereas in CFD, the whole set of equations are referred to as Navier-Stokes equations. And inviscid equations, inviscid Navier-Stokes are called as Euler equations, and the solvers are called Euler solvers. And the equations are for generalized situation, and each individual problem is identified by the flow domain and boundary conditions. As I told, the problems differ from each other, not from the governing equations, but based on the flow domain and the boundary conditions. Okay. And these we have written in matrix form. And as I told, this is called generic form or matrix form or strong conservation form. And here the u is called the solution vector, f, g, h are called the flux vectors, and j is the source vector. And so we can do it with the time marching method, as I told, by taking dou u by dou t this side and taking the other side. Here, if you take it as backward difference, so you are going to get the u in the next time and next time, like that I can march in time. And so this is the solution vector. And from the solution vector, I can extract the primitive variables in this. And so if I have steady Euler equations, right? So it will be of this form. And if I march it in space, then f is the source, the solution vector, which is this. And out of this, as I told, we have to be in a position to extract the primitive variables, because assuming this C1, C2, C3, C4, C5, I should be able to express. As I told, this is a homework for you and it is important, okay, exam point of view. And this is the answer. It is given with the Anderson. You have to solve it. And then this is actually all the equations together we have written in matrix form. In the same way, there is another form. All these called as transport equations, because something is transported, because of that rate of change of some property within the system is equal to local changes and the convective changes like that. These are called as transport equations. So the general form of transport equations can be written something like this. Okay, this is it. Okay, I will write. dou of rho phi by dou v plus del dot rho v phi is equal to del dot gamma del phi plus phi. Okay, this is the generalized equation. All continuity, momentum, and energy equations are there within this. Okay, so if phi equal to 1, so what is the equation we get? Dou rho by dou t del dot rho v, and we are going to get continuity equation, knowing that gamma equal to 0, s phi equal to 0. Okay, and this is called as unsteady term, and this is called as convective term, and this also can be called as local term or unsteady term. This is convective term, and this is called as diffusion term, and this is called as source term. Okay, and so in the momentum equation, diffusion is due to viscosity. In the energy equation, diffusion is due to conduction. Okay, so if phi equal to v, you can see that we can get momentum equation. Okay, and in this equation, gamma equal to mu. Okay, if mu is constant, this will become, okay, del dot mu del v. Okay, so this is going to be mu del square v, like this. And here s phi will have pressure term and body force term, like that. Okay, they are called as source terms. And if you take energy equation, so phi is equal to temperature, and this will get energy equation. And here gamma will be K, thermal conductivity. So here del dot K del T, this is going to be K del square T, like that. And all other terms S phi, that will be source terms. Okay, so except for this unsteady, convective, and diffusion terms, if I push all of them into source terms, so that will be like that. So this is the way, this is a general way of writing all the equations together. And this is done by the great our Indian researcher Patankar. Okay, he is IIT Kanpur product, and later he worked, as I told, in Imperial College London with Spalding, D.V. Spalding. He is a great scientist and writer. He has written books on classical thermodynamics and combustion, like that. And Patankar also has written numerical methods for fluid heat transfer and fluid flow. Okay, this book also I will send you. It is a very, very small book, and he is the one who made CFD popular, commercial, okay, and made this finite volume method very, very easier and comfortable. Okay, so he is a man. He has written all the equations together in this particular form. Okay, and this can be written in the integral form also. That is integral dou by dou t integral v rho phi dv plus the area integral equal to okay, this is gamma del phi. So we will have this is surface integral, right? Like this. Okay, this is going to be if this is area integral, so this is going to be del dot rho phi v, okay, dv, and this is also del dot gamma del phi dv, converting to surface in the volume integral. Okay. Okay, so that is the way we can write it in integral form. Okay, in this way. So as I told, these are area integrals, and del dot of this will become the volume integral, and del dot of this will become the volume integral. And if you can combine, you can get in this form. But this form is used for finite element and finite volume method, and this form is used for finite difference method. Okay, so this is the way it is. And then once we have the generalized equations, then we make various assumptions like I have to simplify the equations. As I told, I cannot completely solve the whole Navier-Stokes equation, and I will try to eliminate some of the dependent variables, or eliminate some of the independent variables, or eliminate some of the terms in the equations like that. Okay, so there are various assumptions like steady or unsteady. So if you assume it to be steady, so what happens? What simplification I get?
Local term eliminates.
Yeah. So we have independent variables x, y, z, and t, and dependent variables we have rho, u, v, w, p, and t. Okay. So steady means this t will go off. Okay. So one independent variable gets reduced. In the same way, compressible or incompressible. Okay, then rho will be constant. So rho is eliminated. One equation gets eliminated. Uniform or non-uniform. Okay, some of the gradients are 0, so you can eliminate some of the terms. Like viscous, inviscid. So inviscid terms can be eliminated. 1D, 2D, 3D. Okay, if it is 2D, z derivatives can be eliminated. If it is 1D, y derivatives and z derivatives can be eliminated. Okay, so laminar or turbulent. Okay, so actually these equations are for laminar in general, or laminar or turbulent, but if it is turbulent, I have to take some additional cautions that I will tell later. Okay, so some of the simplification I am not going in detail, but there are various assumptions like it can be subsonic or supersonic, and some of the forces may be dominant or some may be negligible, like body forces many times we neglect like that, and it can be single or multi-phase. Okay, and if it is like that, there is this number. Sometimes some type of flows will have importance for some type of numbers, and Ca is called capillary number. Okay, Ca is called capillary number, which is viscous force to surface tension force. Okay, sometimes that may be important. Or suppose if it is thermal and density effects, so you have Prandtl number. Okay, so what is Prandtl number? Ratio of. Okay, what is the formula?
Yes, sir. Kinematic viscosity to thermal diffusibility.
Mu Cp by
Some of
K.
the
Cp by K.
yeah, mu Cp by K or mu by alpha, that is easy. momentum diffusivity by thermal diffusivity. Okay, so both are meter square by second per second. Okay, G and the GR is
Grashof number.
Grashof number. Where will it be important?
Natural convection.
Natural convection. EC is
Eckert number.
EC.
Eckert.
Eckert.
Eckert number.
Eckert number. Okay. And so if I have free surface flow, Froude number. Surface tension, Weber number. And here, okay, some more numbers like Reynolds number into Prandtl number. What is this number?
Rayleigh number.
No. Rayleigh number is
Eckert
product of.
number.
Yeah, this is
Nusselt
Eckert number. This is Eckert number.
Eckert number.
And okay, somebody is telling Rayleigh number. What is Rayleigh number?
Grashof into
Yeah,
Prandtl.
Grashof number into
Prandtl.
Prandtl number, like this. Okay. So based on the type of flow, some of the non-dimensional parameters become dominant, and we have to see which forces are to be considered. Okay. Okay, then we talk about boundary conditions. I think in heat transfer you might have already discussed. Can you tell me what are the types of boundary conditions we come across? In heat transfer, what are the things? Have you discussed anything about boundary conditions?
Prescribed temperature, prescribed heat flux,
Yeah, I will tell you. Okay,
and
prescribed
convection.
dependent variable, right? So their temperature is the prescribed the dependent variable. So if we prescribe the temperature, this type of boundary condition is called as boundary condition of first kind. Okay, and this is also called as, a scientist name is there. Anybody knows? Dirichlet boundary condition. Okay, so temperature can be prescribed, or if I have no slip condition, suppose. So what do you mean by no slip condition? Usually velocity equal to 0, right? On the surface of a solid, if there is a flow, due to viscosity, there will not be any slip, and so velocity is 0 on the surface. So that is a no slip condition. Suppose at the inlet conditions, okay? Suppose I have a flow at inlet, I prescribe the conditions, right? Usually they are Dirichlet conditions. I am prescribing the pressure, velocity, temperature, those things at the inlet. So they are Dirichlet boundary conditions. So if you prescribe the dependent variable on the boundary, we call it as boundary condition of first kind or Dirichlet boundary condition. Okay, this is one type. And the second one, somebody is telling what is that prescribed?
Heat flux.
Heat flux.
Neumann boundary condition.
Yeah, very good. So it is called as Neumann boundary condition. And this is also called as boundary condition of second kind. So because Q is equal to, and this is also called as derivative boundary condition. Okay, derivative is prescribed. That is, if Q is given, Qx, suppose, heat transfer in the x direction. So K dou T by dou x is given. That is the temperature of the derivative of the temperature is prescribed. Okay, so this is one example. Suppose I am given that it is insulated boundary condition. Insulated boundary. What do you mean by insulated boundary?
Sir, at that
Heat
point,
transfer.
That is Q is 0. Heat
Q is
transfer is 0. So means derivative is equal to 0. Okay. So insulated boundary is this type of condition. Suppose I have a pipe flow and on the symmetry, okay, the derivative here will be 0, right? The velocity, the derivative will be 0. And suppose I have like this. So at the exit, so usually I have to take it so far so that the dou by dou x of all the properties will be 0. So on the outlet condition, So usually Newman condition. So on the symmetry line, I have Newman condition like that. And sometimes there is what is called as periodic boundary. I will show you some of the examples. Periodic boundary means I have flow in a turbo machine. So I have a cascade. Cascade means, okay, I will have number of blades are there. Okay, so like this. And so the inlet goes in this way, So the flow goes in this way. So what I do is, because it is whatever flow I get here, the same flow I get here, same flow I get here. There is no point in doing the complete whole thing, a big domain. So I can take only a portion of this like this. Okay, only two blades, and this is outstream condition, this is upstream condition like this. Here I prescribe the conditions, and here, and this is called as periodic boundary because it is periodically repeated. So across the periodic boundary also, the normal derivative will be 0 of any property, u, v, p, t, or anything. Okay, so this is also Newman condition. So on symmetry line, on periodic line, you will have Newman conditions. Okay, so this is the second type of boundary condition. And what is the other one?
Convection boundary condition.
Convective boundary condition. Okay, so convective boundary condition means whatever is conducted to the boundary, it is convected. Am I right? This is called as boundary condition of third kind. And this is also called as Robin boundary condition. So if I have a plate like this, okay, so whatever heat is conducted, suppose there is a heat generation here, heating here, something like this. So whatever heat goes to this wall, it is convected out. So what is going there is K dou T by dou X. It is heat by conduction onto this wall. And what is convected out is H into T minus T infinity. So here I equate this K dou T by dou X is equal to H into T minus T infinity. Okay, it is something like K dou T by dou X minus HT is equal to minus HT infinity. It is something like this. So I have, it is a linear combination of, here temperature is there, derivative of temperature is there. So this is a linear combination of first and second kinds, or linear combination of Dirichlet and Newman boundary. Am I clear? Am I clear about this?
Yes.
Okay. So this is called as Robin boundary condition, or boundary condition of third kind, or convective boundary condition. Okay. So this is the way it is named. And there is another thing called as mixed boundary condition. Mixed boundary condition means on a boundary, if up to some surface, if a temperature is given, and up to some surface, it is suppose insulated or something. Okay, so this is Dirichlet, and this is Newman. So if on a surface, part of it is given one type of condition, and part of it is given another type of condition, that is called as mixed boundary condition. And another is Cauchy condition. So Cauchy condition means so one variable will have Dirichlet condition, and another variable may be Newman condition. Okay, so that is on a boundary. Okay, so velocity is prescribed, Dirichlet condition, but temperature it is insulated. Okay, so dou T by dou X is equal to 0. So if one is Dirichlet condition, another is Newman condition for another variable. Such is called as the Cauchy condition. Is that clear? So if both Dirichlet and Newman conditions are specified on the same boundary, it is Cauchy condition. And mixed conditions, if a portion of the boundary is Dirichlet type and another portion is of Newman type. Okay, so these are the different types of boundary conditions. And okay, there are different boundaries. Solid walls are there, inlets, outflows, symmetry, and cyclic or periodic, or there can be a free surface or interface between two different fluids, and far field. Okay, so different types like this. So if you take like this, so this is exit boundary, and this is the inlet boundary. This is actually far field boundary, and here there will be solid walls. This is flow over a sphere or something, cylinder. So here you have no slip, that is velocity is 0. And on the exit boundary, because velocity gradients are 0, this is Newman boundary. And all this, you will have velocity given. So this is Dirichlet boundary. Like that. And suppose I have flow through a pipe. Okay. So again, this is inlet where I am given the velocity. And this is no slip on the wall. So equal to 0, equal to 0. Again, Dirichlet. And on the axis of symmetry, the pressure and the velocity, the gradients are 0. So they are Newman conditions. And at the exit, again, I have derivatives of variables are 0. These are Newman conditions. So I can have the flow through a cascade like this. So this is periodic boundary 1. And on this, I have wall. So wall boundary. And this is inlet boundary. And this is outlet boundary. Like that, I can have different boundaries. Okay, and sometimes I need not take the whole domain. Okay, suppose as I told the turbo machine, if I take, I have number of blades, but I am taking only 2 blades because it gets repeated. Okay, they are periodic. In the same way, suppose I have a flow like this. Okay. So choosing the appropriate boundary condition can reduce the computer effort. In this example, a slice, okay, a sector like this. If I take only a sector here, okay, so that sector and next hole also will have a sector. It will have same type of flow. Okay, so I can solve only this particular sector instead of taking the whole 2 pi radius of that. Okay. So figure 1 is repeated to produce the whole physical domain using the periodic boundary condition at the imaginary planes. So the figure 2 can reduce the computational domain to a much smaller area. Okay, so if I assume this as periodic boundary and this is periodic boundary, and if I substitute the boundary conditions, then I can get the whole one. So I need not take the whole domain. I can take only a small sector of the domain. Is that clear?
Yes, sir.
Yes, sir.
Okay. So that actually completes the first chapter about the governing equations and the boundary conditions. Okay. So then we go for what is called as partial differential equations. So many times I write the derivatives as suffixes like ux is dou u by dou x, phi xx, dou square phi by dou x square, like that, so that it will be easier for me to write it. Okay, and we see classification. So what are the various classifications? Can anybody help me?
Elliptic, parabolic, hyperbolic.
Okay, that is one. Okay, I will tell you the order of the equation. That is, I will have third order, second order, first order, like that. So how do you decide about that? Based on the highest order derivative present in the equation. Okay, I can have uxx or uxxx ux only. So this is first order, this is third order, this is second order, like that. Second order derivative, dou square u by dou x square, dou cube u by dou x cube, dou u by dou x, like that. If I have the highest order derivative, this will be taken as the order of the equation. Okay, and then the second one is degree of equation. Suppose I have some uxx plus 3 ux square plus 4ux equal to 0. So what is the degree of the equation?
1.
It is 1 only. Okay, sometimes you may think it is 2. It depends on the degree of the highest order derivative. Okay, so this is 1 only. Suppose if I have uxx cube plus 4ux plus 3 equal to 0, something like this. So it will be third order equation. Third degree. Okay, third degree, second order. Do you understand the difference between order and degree? Degree is the power. The power of the highest order derivative will be taken as the degree of the equation. Is it okay?
Yes, sir.
And there is another thing like homogeneous or non-homogeneous. Okay, so if all are only derivative terms, okay, then it is homogeneous. And if there is a term only of dependent variable without derivative, then it is non-homogeneous. Okay, I will write some example like suppose I have generalized equation. I will write again later a phi xx plus b phi xy plus c phi yy. Second order, the complete equation b phi x plus c phi y plus f phi plus g equal to 0. This is general second order equation of two independent variables. That is x, y are the independent variables and phi is the only dependent variable. Okay, and a, b, c, d, etc. are functions of x and y. So a, b, c, d, e, f, g are functions of x and y. Okay, so if g equal to 0, then it is homogeneous. This is g of xy. Okay, there are only independent variables. Okay, that is, it is only a function of x and y. There is no phi here, no phi. Okay, so if this term is present, then it is non-homogeneous. If this is not there, all are with dependent variables only. If there is a term only of independent variables. Okay, this is the term of only independent variables. Then this is non-homogeneous. If this is not there, it is homogeneous. Could you understand the difference? All terms have dependent variables and independent variables, but if there is one term with only independent variables without any dependent variable, then it is non-homogeneous. If this is not present, then it is homogeneous. Okay, that is the way. And then another important thing is linear or non-linear. And there is another thing also called quasi-linear. Okay, we will see here. And if there is any product of dependent variables or its derivatives, then it is nonlinear. Okay, if suppose I have 5x square, okay, this is nonlinear. 5x, this is nonlinear, and 5 square is nonlinear. Okay, this is product of dependent variables, and product of dependent variable and its derivative. This is products of dependent variable derivatives. So these types of terms are nonlinear. Okay, suppose I have u dou u by dou x and v dou t by dou y. These are nonlinear. Is it clear? Even dou of u square by dou x. This is nonlinear. All these are nonlinear. Could you understand?
Yes, sir.
Okay. So this is the way we define. Okay, as I told, the advantage of linear is what is called as it follows law of superposition. Okay, and it is something like if you remember, I have an equation like b square minus 4 into y is equal to some f of x. Okay, something like this. If you remember the linear equations when you have solved in your BTech. Okay, so this is the way. And so this, it will give you, there is what is the total solution. Y is equal to some CF and PI. What is CF?
Complementary function.
Complementary function, and PI is
Particular integral.
particular integral. Now can you tell me what is the complementary function?
Yes, sir. Your
D1
D
is
is equal
power
So
to
D is equal to plus or minus 2, right?
Y.
Yes,
अच्छा,
sir.
sir.
Yes, sir. For that we have to calculate auxiliary equation.
So what is that we will get here?
C1 e to the power 2x plus C2 to the power
C1
minus
e
2x.
power 2t, it's a 2x plus
C2
C2 e power minus 2x. Okay, and this is called as complementary function. What it is meaning is e power 2x is the solution for this equation. E power minus 2x is another solution for the equation. And any linear combination of these two solutions also is a solution. Okay, you give any value for C1 and C2, this will become another solution. So all these linear combinations, superposition of those solutions also is a solution for the equation. This is called as law of superposition. Particular integral also is a solution. CF is also a solution. And so the sum of these two also is a solution to the original equation. Am I clear?
Yes, sir.
So this is called as law of superposition. But now for nonlinear equations, it's not true. Okay. So another characteristic I told the difference is here any small change in the boundary conditions will bring a proportional change in the solution. But in nonlinear, any small change in the conditions will give a unexpected change in the solution. And this is, as I told, it satisfies butterfly effect. It has the characteristic of butterfly effect. Okay, so that is about linear and nonlinear. And the other is, as somebody is telling, elliptic, parabolic, and hyperbolic. So this is based on the characteristic. That is the solution course. Okay, so we will see some example. We take again the generalized second order partial differential equation with two independent variables and one dependent variable. So same thing as I have told you, a phi xx plus b phi xy plus c phi yy plus d phi x plus b phi y plus f phi plus g equal to 0. This is the generalized equation I take. Okay. So the solution I am going to get as phi is equal to phi of xy. Okay. And if it is a single one variable is there, then it will be phi equal to phi of x like that. So x phi, it will be a curve. Okay, it is a curve on a two-dimensional graph. Okay, but this is because it is two independent variables are there. It will be a space curve. Okay, these are space curves, and this is called as characteristic. Okay, so the characteristic of characteristic is the second derivative along characteristic is indeterminate, and second derivative across characteristic is discontinuous. So this is the characteristic of characteristic. Okay, so this you have to remember mathematically. And so I want to get the expression for second order derivative. And how to get that? I have one equation. There are second order derivatives. How many are there? Phi xx, phi xy, and phi ya are there. So I want two more equations. And I want to generate from the principles of derivatives. So what I do is, if I want to take, if you remember, if u is a function of xy, so what we are writing, du is equal to dou u by dou x dx plus dou u by dou y dy, like that. In the same way, I can write d phi x is equal to dou by dou x of d phi x into dx. Dou by dou x of d phi x is phi xx dx plus phi xy dx. Like this, I am generating an equation with mathematical principles. In the same way, I can write d phi y, that is dou by dou x of d phi is phi yx dx plus phi yy dx. Like this. So this is one equation, this is second equation, this is the third equation. And the first equation I will write in another form. I will write this as a phi xx plus b phi xy plus c phi yy. I will take all these things to the, sorry, not this, all these things to the other side. I will write it as some h. So h is equal to minus d phi x minus e phi y minus f phi minus g. Okay. So I am taking all to the other side. So I will get this way. So I have three equations, and the unknowns are phi xx, phi yy, phi xy, and phi yy. These are the three unknowns. And if I want to find out the expression for the second order derivative, I use Cramer's rule. So how can I get by the Cramer's rule? Phi xx is equal to, it is ratio of two determinants, right?
Yes, sir.
What is the denominator? coefficient matrix, right? Denominator will be the coefficient matrix. And what are the coefficients? A, B, and C for the first equation. For the second equation, what is the coefficient of phi xx? That is dx, right? And what is the coefficient of phi xy? That is dy. What is the coefficient of phi yy? 0, right? There is no phi yy term. That is 0. And in the third equation here, what is the coefficient of phi xx?
0, sir.
0. And phi xy?
Dx.
Dx. And phi yy? Dy. Okay, like this. This is the coefficient matrix. And in the numerator, what should I do? How will I get phi xx?
Augmented one.
Deleting dx, the coefficient of dx.
One column I have to replace by the right hand side matrix, right?
Yes, sir.
So this a dx 0, I have to put the right hand side. What is the right hand side of the first equation? H, right? And the second equation, d phi x. Third equation, d phi y. And the remaining will be as it is, d, c, dy, 0, dx, dy. Right. Am I right? Okay, this is the way we write. We can write for a phi xy, phi yy and all. But what we have seen is characteristic is the one along which the second derivatives are indeterminate. So when will this become indeterminate?
Denominator is 0.
Denominator is equal to 0. That is, this determinant should be 0. If this denominator is 0, all the three derivatives phi xx, phi xy, phi yy will be indeterminate because denominator is same for all. Okay, so this is 0. A, B, C, dx, dy, 0, 0, dx, dy equal to 0. Okay, this gives the characteristic direction. A, B, C, dx, dy, 0, dx. And expand this. So if you expand this, A dy square, right? And minus B into dx dy and plus C into dx whole square equal to 0. Am I right?
Yes, sir.
And divide this by dy whole dx whole square. So I am going to get A into dy by dx whole square minus B dy by dx plus C equal to 0. So I want to know the characteristic direction. So dy by dx is equal to B plus or minus root of b square minus 4ac. So it depends on the b square minus 4ac. So if b square minus 4ac is less than 0, okay, so no roots, okay, no characteristics, and this type of thing is called as elliptic equation. If b square minus 4ac equal to 0, then
Hyperbolic.
Parabolic.
parabolic.
Parabolic, sir. Yes, sir.
So what happens? I have only one real root. Am I right? Because this is 0,
Yes, sir.
b by 2a, there is only one real root, one characteristic. If b square minus 4ac is greater than 0, two real characteristics.
Hyperbolic.
Yeah, two real characteristics, and this is called as hyperbolic. Okay, this is the way. And okay, only one thing, don't get confused that the curves may be elliptic or parabolic or hyperbolic. Why it is named is, if you see the original mathematics, if you see general equation, ax square plus bxy plus cy square plus dx plus ey like that. So there, an elliptic
Sir,
function, yes,
sir, in first case, b square minus 4ac less than 0.
yeah.
No roots is
Means
exist, no?
roots imaginary, okay, I can say.
Imaginary complex roots
Yeah,
is
roots
exist.
are imaginary. Okay.
Yes, sir.
No real roots. What I want to say is no real roots. Okay, roots are imaginary. So in the mathematics, that for general equation, like as I told you, a y square plus bxy plus cx square plus dx, like that, if I have b square minus 4ac, if it is 0, then it is parabola, and less than 0 it is ellipse, and greater than 0 it is hyperbola. So based on that, it is named like this, but it has no physical meaning in writing ellipse or hyper. There is no curve like ellipse or hyperbola or parabola. Okay, so that is important. Okay, this is the way. And physically, what is the difference? Okay, and we'll see one thing. If I take 2D velocity potential equation, okay, you will get and steady. You will get something like 1 minus m square 5xx plus 5yy equal to 0. This is a two-dimensional velocity potential equation. If I have 3D plus 5zz will be there. Okay, it doesn't matter. So here, if I ask you, what is this equation? Ellipse, elliptic, parabolic, or hyperbolic? So here we have to see what is ABC. Okay, so if you see the coefficient of phi xx, a equal to 1 minus m square, and the coefficient of phi xy is 0, there is nothing, and coefficient of phi yy is 1. Okay, so now if I see b square minus 4ac, so what will I get? Minus 4 into 1 minus m square equal to 0, or 4 into 1 minus m square equal to 0, or 1 minus m square equal to 0. So it depends on the value of m, okay, whether it is less than 0 or greater than 0. Okay, if m is less than 1, as I told, this is subsonic. So if m is less than 1, what is going to happen? 1 minus m square is
Positive.
less than 0. It is positive, right? Sorry. 1 minus m square is m square minus 1 or 1 minus m square? Just b square minus 4ac, that is 4 into 1 minus m square equal to 0 or m square minus 1 equal to 0? Actually, we will get m square minus 1 equal to 0. Right? B square minus 4ac, 4 into 1 minus 1. No, actually it is 4 into m square minus 1 equal to 0. So m square minus 1 equal to 0. Actually, there is something mistake. So m square minus 1 equal to 0. Okay. So if m is less than 1, m square minus 1 is less than 0. So this is elliptic. If m equal to 1, that is sonic, then m square minus 1 equal to 0, and this is parabolic. If m is greater than 1, that is supersonic, then m square minus 1 is greater than 0, and this is hyperbolic. So you have to remember this: subsonic elliptic, sonic parabolic, and supersonic hyperbolic. Okay, so this is mathematically. I will show you what happens. Okay, suppose there is a flight moving. Okay, there is a flight moving, or the train. Okay, and it is going with subsonic velocity. Okay, it is somewhere here, and this is moving with subsonic velocity. So when it is moving, it creates sound waves, right? Sound waves will be moving. And what is the sound velocity? So that is A. Okay, maybe some 330 meters per second. Okay, so this may be going less than 330 meters per second. So it is going with 100 meters per second. And after some 4 seconds, and how much it will go? After 4 seconds, some 400 meters per second. So for the first second, second second, third second, and fourth second, it will come here. And so what happens is, at this point, it creates some sound because it's starting, it creates sound wave. And how much distance this will go? The sound wave. It uniformly goes in all directions like a circle. And after 4 seconds, the initial sound wave goes in 330 into 4. From 1320 meters it will go. It will make a very big circle. Am I clear? And at this point also, at every point, it is creating some sound waves. So whatever sound wave it has created at this point, it will go 3 seconds, right? 3 into 330, 990 meters per second with this as center. Okay, so it is going to be something like this. And whatever it is producing here, it goes 660 meters per second with this as center, like this. And again, whatever it has produced here, this goes to 300 meters per second, like this. So there will be number of circles produced like this. And
Sir,
yes,
sir, I don't understand that.
okay, it has created one sound wave here, which travels by 4 into 330 meters per second. By the time the train reaches this point, first point, last point. Am I clear or not? Train has
Yes.
come this distance, but the circle will be very large. Okay, and whatever sound wave is produced at this point will make a 990 meters per second circle. Am I clear or not?
Yes, sir.
So like that, I will have circles, and always the circle will be ahead of it. Actually, though it is, I didn't draw such a big circle. I will show you. Maybe slide may be there. I will show. Yeah, this is the way. Okay, the first circle, and after this point goes to this point, it creates another circle. When it goes to this is a small circle, like that. We will have number of circles, and you can see that the sound waves will go very far and it will be inside. Okay, so uniformly it is going out. There is no particular direction for it. It goes in all directions uniformly. Okay, so this is a subsonic flow, and this is called as zone of disturbance, and this is zone of disturbance. And outside this circle, if I stand here, I will not hear any sound till this circle reaches me. This is zone of silence. Am I clear? And the
Yes.
train will be always within the zone of disturbance. Okay, train will be always within the zone of disturbance. And another thing, suppose I am a blind person, okay, and I want to cross the railway track. Okay, and train is coming from far. So I will listen to the sound before the train reaches me, and I know that train is coming, and based on that I can estimate how much distance it is, and I can cross it. There is no problem, right? That is subsonic. Suppose the train is moving with sonic velocity. So what happens if initially it is there and it goes to this point, and whatever distance it has gone, actually the circle, the zone of that is disturbance actually goes like this. Am I right? This also goes to the same distance. Am I right?
Okay, sir.
And once it goes to another point like this, so the first wave becomes like this, and the second wave, which is started from here, right, it becomes like this. And when it goes to another second like that, so if I show it this way, okay, so if it goes like this, the first wave, it is like this, second wave, it goes like this, and third wave, and actually nothing goes beyond this train. Train is here, right? Because the wave also moves with the train. Nothing, because the sound wave will not go faster than the train. Am I right? So the whole region divided into two zones. This is zone of disturbance, and this is zone of silence. And even if I am just standing here, I will not know. Suppose the train is coming, I want to cross the train. Till it reaches me, I will not hear the sound, because the sound is coming with the same velocity as the train, right? If I want to cross it, if I just cross it, it will hit me. Am I right or not?
Yes, sir.
Okay, so there is only one characteristic. All of them, it is just similar to normal shock. Each is a small pressure disturbance, and all the pressure disturbances together, if you see, so there is more pressure difference across this. Okay, so there are so many pressure waves. There are so many pressure waves, and each pressure wave will have a small pressure difference, and all of them clubbed together here, there will be large difference will be there. So it is like normal shock. This is like normal shock. Am I clear? And this is the characteristic. Okay, one real characteristic will be there, and this side completely silence. This side is completely zone of action or disturbance. Okay, now if it is going with supersonic velocity, okay, so by the time it reaches here, the first wave, it will take a very large circle, because it is okay, this is the circle, but this train is moving faster than the sound. Am I clear? So suppose this last wave, it is making this circle, but this train is ahead of the circle. Okay, the first wave goes like this, second wave goes like this, third wave goes like this, but this train is before all the waves. Okay, so if you see a boat going in a sea, okay, it will make disturbance like a V shape. So in the same way, you will get that waves. These are actually oblique shocks. These are oblique shocks. Is this clear? And the zone of disturbance, it is confined to these two characteristics. These two are characteristics. And this is like a cone. Okay, in 3D, this is like a cone. This is, okay, sometimes we call it a sonic boom. Okay. And the thing is, if I am so this is the train of flight, and this is zone of disturbance, and this is zone of silence. And suppose I am standing here, okay, I will not listen the sound. Even though it crossed me, I will not listen the sound. Okay, this is here, but I am here behind. But still, unless this I am in the zone of disturbance, I will not know. Only when this train goes here, when the cone comes here, and if I am within that, then only I will listen. Is that clear? So sometimes what happens is, if there is a passenger aircraft is going over your building, and you will listen the sound, and in childhood we are interested to see that flight. I go to the staircase, and when I go to the staircase, I will see it is coming from far. Okay, so I can stand there, it will come and cross me like that. Because I am in the zone of disturbance, it goes with subsonic velocity. So when the circle crosses my building, I listen to that. Okay, as long as I am in that circle, I listen to the sound. But if it is going with supersonic velocity, like jet, okay, jet plane goes like that. Okay, so you will see it goes with a very height, and you see it is a small one, and you can see the streaks coming behind it. So that is normally jet plane. Jet plane goes with supersonic velocity. So when you go up, you will see that it is already gone there. Okay, then only you will listen the sound, because it is in the supersonic velocity, and only when you are in the cone of disturbance, then only you will hear the voice. It is already gone beyond your building. Am I clear about that?
Yes, sir.
Okay,
Yes, sir.
so
Yes, sir.
this is the difference. This has two characteristics. Okay, if it is a 2D, I have like this. These are the two characteristics. Okay, this is about this. And so if you see some examples, elliptic trace. Okay, you can see that Laplace's equation. So what is Laplace's equation? Del square phi equal to 0, or phi xx plus phi yy equal to 0. So if you see a equal to 1 and b phi xy is not there, so b equal to 0, and c the coefficient of phi yy is 1. So b square minus 4ac, what is this? 0 minus 4, which is less than 0, which is elliptic. Okay, so Laplace's equation and even Poisson's equation, which is suppose del square psi is equal to minus 1. Okay, so this is called as Poisson's equation, and this is also same thing, elliptic, because whatever is there on the right side, it doesn't matter. This is psi xx plus psi yy is equal to minus omega. So again, b square minus 4ac less than 0. So we know that this is for 2D incompressible irrotational flow. So this flow is elliptic type. And similarly, stream function equation for incompressibility. So this is Poisson equation, and that is elliptic. Okay, some examples we can see like that. And if you see parabolic, it is something like if I see like this. Okay, so this is unsteady 1D heat conduction, isn't it? That is that. So if you see here, okay, Txx only is there, and A is equal to alpha. And Txy is not there, Tyy is not there. Here, if this is y, okay, xt is not there, and tt also is not there. So b equal to 0 and c equal to 0. Am I right? There are two independent variables, x and t. There is no txt is not there, ttt is not there. Okay, so b and c are 0. So So b square minus 4ac is equal to 0. So this is parabolic. Similarly, if I take momentum equation, okay, so if it is unsteady, viscous flow and 1D, so you will have like this. Okay, so this is unsteady 1D viscous flow. Okay, so we will have not alpha, here mu. Okay, so A equal to mu, B equal to C equal to 0. So B square minus 4AC equal to 0. So this type of equation, they are parabolic. And usually unsteady equations are considered as parabolic in nature. Or the time derivative is parabolic in nature. Okay, means it has only one characteristic. Okay, past is zone of disturbance and the future is zone of silence. Am I right? So I don't know what is going to happen in the future, that is time greater than the present, and time less than present, we know everything what happened, that is zone of disturbance. So time has parabolic nature. Okay? And the diffusion term has elliptic nature. Okay, diffusion means suppose a disturbance made here, right? It diffuses throughout the field uniformly. Okay, it is elliptic nature. In the same way, something is heated, the heat is conducted uniformly throughout. So the diffusion term k del square T or mu del square U, okay, or mu del square V, they are elliptic in nature. Diffusion term is elliptic in nature. Time derivative is parabolic in nature. Is it clear? And coming to hyperbolic, okay, so I take what is called as 2D wave equation. Two-dimensional wave equation. What is 2D wave equation? From UTT is equal to A square UX, where A is the sonic velocity. Okay, UTT A square UXX. And so here, if I write this as UTT minus A square UXX equal to 0 like this, and so A equal to 1 and B cross derivative is not there, 0, and C equal to minus A square. So B square minus 4AC is B square 0, it will be 4A square. A is sonic velocity, which is positive, so this is positive and this is hyperbolic. Okay, this is hyperbolic in nature. And already we have seen that supersonic velocity also hyperbolic in nature. Okay. So this is the way we can see some of the examples. Actually, first order wave equation also is there. And this we call it as, we will write it as UT is equal to AU. This is first order wave equation. This is also hyperbolic. And why we call it as, we can get this equation, second order wave equation from here. Suppose I take the time derivative of this sec. Okay, so I'm going to get UTT is equal to AUXT. I will write this as AUT of x. Actually, this is UT, sorry, I have written wrong. UT plus AUX equal to 0. Okay, this is first order wave equation. Or UT is equal to minus AUX. Okay, so this will become UTT minus AUXT, like this. So minus A and UT, if I substitute minus AUX here, yes. So this will become plus A square UX. Okay. So I am going to get from this equation UTT is equal to A square U. Both mean same. Only thing is it is having first order derivatives and this is having second order derivatives. Okay, so this is called as first order. It is we don't say 1D, first order wave equation. This is second order wave equation. If I don't say 2D. Okay, this is the way. This is the hyperbolic equation. Am I clear about this? Oh, I have gone beyond a lot time. Nobody has indicated me. Okay. So this is for second order derivatives, but how to classify first order derivatives, we will see in the next class. We'll stop here. We'll continue in the next class, and just quickly we will go through a small story. So it is an inspiring story of Glenn Cunningham. Who is the next class? Who is taking?
EMTE.
Sir, EMTE.
Okay, Srinivasa sir only. Okay, he is by my neighbor only. I will tell him to take after 5 minutes. Okay, so this is Srinivasa sir. ఒక 10 నిమిషాల తర్వాత తీసుకోండి క్లాస్. Okay, so he will take after 10 minutes. 10. Okay. So here, once a young school boy was caught in a fire accident in his school and was assumed that he would not live. His mother was told that he was sure to die, for the terrible fire had devastated the lower half of his body. Even if he were to survive, he would be a cripple throughout his life. That's what she was told. But the brave boy did not want to die, nor did he want to be a cripple. Much to be the amazement of the doctor, he did survive. Okay, they thought he will not survive, but he survived. But unfortunately, from his waist down, he had no motoring ability. His thin legs just dangling there, lifeless. Ultimately, he was discharged from the hospital. But his determination to walk was indomitable. Right? He wanted to walk, but it's not helping the body. At home, when he was not in bed, he was confined to a wheelchair. One day, when though nobody was there, he threw himself from the chair down onto the floor and pulled himself across the grass. He tried to crawl, right? And dragging his legs behind him. He reached the picket fence. Up to fence, he has dragged himself, and he caught the fence. He raised himself up, and then stake by stake, he began dragging himself along the fence. His resolve to walk was undeterred. He did this every day. He was practicing every day, with faith in himself that he would be able to walk unaided. With his iron persistence and his resolute determination, he did develop the ability to stand up, and then to walk haltingly, then to walk by himself, and then to run. Okay, so but he can understand what hell of pain he has gone through all those days. And then he began to walk to school, then run to school, to run for the sheer joy of running. Later in college, he made the track team. In February 1934, in New York City's famed Madison Square Garden, this young man, who was not expected to survive, who would surely never walk, who could never hope to run, This determined young man, Dr. Glenn Cunningham, ran the world's fastest mile. An epitome of the power of positive thinking and faith in oneself, Glenn Cunningham continues to be the inspiration for many, and his story a brilliant testimony to how one can bounce back even when all odds are stacked against one, to the extent that death seemed the preferable option. Okay, so this is Glenn Cunningham. In running, it is man against himself, the cruelest of opponents, ourself only. The other runners are not the real enemies. His adversary lies within him, in his ability with brain and heart to master himself and his emotions. Okay, thank you. Thank you very much. See you again.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank
Sir,
you.
thank you,
So
sir.
10:10 class will start. Okay. Next class.